So welcome everybody to this latest A2 trigonometry video, and in this video we'll be going through the proof of the compound angle identities, also known as the trigonometric addition formulas. Now, because we've already looked at right angle trig, obviously we've got two right angle triangles here, but the triangle that's created with the compound angle is not right angle. So the first thing I probably need to do is turn this compound angle where it is involved in a right angle triangle. So what I'm going to do is I'm just going to draw a perpendicular line through OA that connects to P. So this is now our right angle triangle, and all I'm going to do is I'm going to label this point here B, this point C, and I can then also, although a bit of a spoiler, and turn another right angle triangle here, and let's call this R. So from this particular diagram, we're breaking up the original diagram of OPQA. I've now created another diagram which involves a lot more miniature right angle triangles, which are now going to help prove the identities for these compound angle formulas. So let's start by proving the identity of sine alpha plus beta. Now, the key things to remember when we're dealing with sine alpha plus beta, which is this angle here, is to work with sine, we need opposite over the hypotenuse. So what we're looking at is we're looking at this length here, which is what I'm needing. Because then from finding that, what I can then know is that sine alpha plus beta is going to be equal to the length of P to B over 1. So then we get our angle. So that's what we're going to go on to work out this length of the blue line, so we can then work out what sine alpha plus beta is going to be. Now we're going to do this in stages. So what I'll do is I'm just going to get rid of all of this, but PB is exactly what we are trying to find, and once I've found PB, I can then work out what sine alpha plus beta is going to be. And we're going to do this in relatively quite small steps. So to start off with, and I'll refer back to that diagram, and let's use a pen that actually comes up on the screen. So the first thing let's work out is the distance of P to Q. So let's work out what this length here is going to be. Now if I take that triangle out, and let's just draw a smaller triangle, and so this here is beta, this is 1, and the triangle we're looking at is O, P and Q. And this is what I'm trying to find. So from this we can then see that sine beta equals PQ over 1. So P to Q equals, let's put therefore. So therefore P to Q is going to equal sine beta. So from my diagram, what I can do is I can label this as sine beta. Now the next thing I'm then going to find, number 2, is work out what O to Q is. So again, I'm going to draw a triangle taken from that mega diagram. So I've got P, I've got Q, and I've got my angle, which here is beta. I've got 1, and this is O. And what I'm trying to find is what this length here is going to be to O to Q. So for this, I need to do that cos beta is going to equal O to Q over 1. So therefore O to Q is going to be equal to cos beta. So from my diagram, this length here is going to be cos, I'll spell it backwards, is going to be cos beta. So from that triangle of OPQ, I've worked out what the 3 lengths are now going to be. So the next thing for me to do then is, once I've worked out O to Q, is to work out what Q to A is going to be. So from this, let's now work out what Q to A is going to be. So from that bottom triangle, I now know that this angle here is going to be alpha, and I've got that this here is cos B, and let's just label the vertices of O, Q to A, and Q to A is what I'm trying to find. So here I've got sine alpha equals, and it's going to be opposite, which in this case is Q to A, over the hypotenuse, which is cos beta. So therefore Q to A is going to equal sine alpha cos beta. So from this diagram here, I can label this diagram as, and just double check to make sure that I've got it correct, it's sine alpha cos beta. And q to a to q is the same as this length here. So again, I'm just going to write this as, I don't know, I keep starting with cos. So this length here is also sine alpha cos beta. Now, from this, what I then need to do is work out the angle. So the only thing left for me to find, remember that our main objective is to find the length of P to B. So all I've now got to find is what this here is. So this blue line here. So now I've got a right angle triangle, but obviously in order to use trig, I need to know what one the angles are. So for this, what I need to do is try and use my knowledge of sort of angles in right angle triangles and parallel lines. So here, if this angle here is alpha, then the angle, which I'm just going to write here, so angle, or let's not even write angle, let's use proper notation. So let's go for, let's go for yellow. So the angle, if QOA equals alpha, then angle QOA is going to be equal to the angle of RQC. Why? Because they are alternate. Now from this, so we worked out that this angle here is going to be alpha, and that's going to be a right angle. Now looking at the triangle of PQC, so PQC, that this angle here, therefore, so this angle here is going to be equal to 180 minus 90, so right angle minus alpha. So that's what this angle here is going to be. Now from that, so if I just write this out, so angle PCQ is going to be equal to 90 minus alpha. So from that, I can then work out what this angle here is. So this angle here is going to be equal to, and again, treating it as a right angle triangle, that if this angle here is 90 minus alpha, and this is the angle that I'm looking for, that this angle here is going to be 180 minus 90, which is the right angle, minus 90 minus alpha. And simplifying all of that just leaves me with alpha, so this angle here is going to be alpha. Now from that, what I can then do is take this triangle, and that's probably quite a pathetic little loop there. So what I'm going to do is I'm going to take this right angle triangle of PRQ, because obviously what I need to do is find what P to R actually is going to be. So in terms of my next step, so if I just take that triangle out, I know that this angle here is alpha. This is the length of P to R, which is what I'm wanting. And I know that this length here is sine beta. So, and what I'm trying to do is find what the length P to R is. So using the adjacent and the hypotenuse, so I've got cos alpha is going to equal P to R, which is what I'm wanting, over sine beta. So therefore, P to R is going to be cos alpha sine beta. Now if I go back to my diagram, let's just get rid of this little purple loop. But I've then worked out that this distance here, this blue line, is cos alpha sine beta. So although it looks very messy, what I'm going to take out from this is this triangle here. Now if I just get, so looking at this triangle, and just emphasize that that's what we're looking at, what I found, and again just creating a bit of space, if I just draw that triangle out, that this angle here of alpha plus beta, we know that this is 1. Now I've split up into two sections, So this first section was from B to R. Just write B to R so you can see what I'm talking about. And that length there was sine alpha cos beta. And that's what this length here was. And this length here we discovered was cos alpha sine beta. So therefore that sine alpha plus beta is going to be equal to the opposite over the hypotenuse. Now if the opposite is going to be those two things added together, so the opposite is sine alpha cos beta plus cos alpha sine beta all over 1. So therefore we know that sine alpha plus beta, that compound angle, is going to be equal to sine alpha cos beta plus cos alpha sine beta. And there we've proved one of our identities. Now when it comes to proving the identity of cos alpha plus beta, now again if we think back to the cos formula, in order to work with cos, what I need to know is I need to know the adjacent and I need to know the hypotenuse. Now if I take the triangle of POB for starters, then obviously I need to know what the adjacent is going to be of that triangle. So in order to work out alpha plus beta, what I need to do is I need to work out what this length here is going to be of our triangle. So I'm needing OB over 1, and then I can work out what cos alpha plus beta is going to be. Now OB is going to be equal to OA minus the length of RQ. And these are the two lengths that I need to find. So starting off with this then, let's work out, well, looking at OA, so if I look at, just writing it here, so let me just put a little space here. So in terms of finding OA, so here I've got my triangle and I've got alpha. I know that this length here is going to be, well, that's O to A. This is going to be cos beta. And what I'm needing is the adjacent, so let's just call this O to A. So in terms of this, I've got cos alpha is equal to the adjacent, which is OA, over cos B. So therefore, O to A is going to be equal to cos alpha cos beta. So that's what this length here is going to be. Now in terms of finding what R to Q is, so again if I get a different colour, so finding out what this length here is, so if I put find R to Q and I take that triangle of P R Q, and it's this length here that I'm trying to find, so let's just call that RQ. I know that this length here is sine beta and this angle here, which is alpha. Now looking at that triangle and just orientating it, I get that sine alpha is equal to, so the adjacent, the opposite, which is RQ, which is what I'm wanting, over sine beta, which is the hypotenuse. So therefore RQ is going to be equal to sine alpha sine beta. Now taking this and this into this, because obviously I want to know what AB is, then the triangle that I get, and again if I just scroll down and draw that triangle, so this angle here is alpha plus beta, this length here is 1, and again just labeling that triangle up again, I've got B and that top is P. I then worked out that this length here is going to be equal to OA, which is cos alpha cos beta, minus O to B, which I worked out as being sine alpha sine beta. And there I've then gone on to prove that cos alpha plus beta is going to be equal to our adjacent over hypotenuse, so it's cos alpha cos, let's actually write it properly, don't want my C's turn into B's. I've got cos beta minus sine alpha sine beta all over 1, which gives me cos alpha plus beta equals simply cos alpha cos beta minus sine alpha sine beta, and there is my second identity. Now, when going on to prove the identity of tan alpha plus beta, I don't actually need to reference the diagram. However, because obviously we know that the identity of that tan theta equals sine theta over cos theta, I'm going to use the previously proved identities into this sort of trig ratio. So here we know that tan theta equals sine theta over cos theta. So therefore tan alpha plus beta is going to equal sine alpha plus beta over cos alpha plus beta. Now if I then use the trig identity that we've already proved, so sine alpha plus beta can be written as sine alpha cos beta plus cos alpha sine beta, and I can write cos alpha plus beta as cos alpha cos beta minus sine alpha sine beta. Now from this, if I then divide all the terms, so what we're now going to do is divide each term by cos alpha cos beta, then what we end up with, so if I just label this as number 1, so for number 1 what we're going to get is we're going to get sine alpha cos beta over cos alpha cos beta. Then with this second term I end up with cos alpha sine beta over, and it's cos alpha cos beta. Then with this term, now moving on to the denominator, so I end up with cos alpha cos beta over cos alpha cos beta, and pick another colour, so this one here got minus sine alpha sine, what's going on there, I've got sine beta over cos alpha cos beta. So all I've done there is done that. Now what I'm now going to do is simplify each of those 4 terms. So again, taking full range of these, so simplifying this box here, then what I find is my cos and my cos betas will both cancel for both from the top and the bottom. So all I'm left with is sine alpha over cos alpha. If I then look at and simplifying this red box here, then you can see that all I'm going to be left with is basically the cos alphas are going to cancel, and so all I'm left with is sine beta over cos beta. With this box here, just note that basically all the terms cancel, so that just equals 1. And for this here, if I simplify this, then what I'm left with, well, sine theta, well, sine alpha cos alpha. So if I treat this as, let me just write it out again. If I split those up, then what I end up with is sine alpha over cos alpha times sine beta over cos beta, which then low in tails becomes tan alpha times tan, I don't know what scribble there, over tan beta. So then what I'm left with is just that. Now from this, what I can then do is simplify this as tan alpha plus, simplifying this as tan beta over, and then keep the denominator same. I've got tan alpha tan beta, and that's what equals tan alpha plus beta, and there is my third identity proved. Now that is something that is on the syllabus that you are going to need to know how to prove. But you can see by taking the simple trig identity of tan theta equals sine theta over cos theta, merge the two identities of sine alpha plus beta and cos alpha plus beta, and it just becomes a sort of cancellation and notation sort of way. But the key step to remember is that once you've gone from the trig identities, substitute them in, is just divide every single term by cos alpha cos beta, and then it just becomes a simple algebraic sort of fraction for you to simplify. So now let's have a look at when your compound angle is created by taking away one large angle away from a smaller angle. So in this case, let's have a look at proving what sine alpha take away beta is and what cos alpha take away beta is going to be. Now, in terms of this, we know that, and just got the pen, we know that sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. Now if, let's say, we're looking at sine alpha take away beta, then that's basically sine alpha plus minus beta. So all I'm doing here is just going to replace beta with a minus beta instead. So what would that look like? Would it look like sine alpha cos minus beta plus cos alpha sine minus beta? Now let's have a look at what cos minus beta actually is. Now in terms of this, let's have a look by looking at the graph. Now this is a very poor cos graph. Let's just do y, and here is my going to be cos x. So from this, what we've got is we're going to end up with, let's get a colour that's actually going to show. So my y equals cos x is going to look like that. Now if I was to then go on to plot y equals cos of minus x, or in this theory minus beta, then look, remembering our graph transformations, all we're doing here is reflecting upon the y-axis. So if I reflect that graph on the y-axis, you can see that the two curves, unlike my diagram, are actually going to be exactly the same. So here, cos of minus beta is going to be the same as cos beta. So rather than writing sort of this, what I can then do is write sine alpha cos beta plus cos alpha sine minus beta. Now if I then look at what sine minus beta actually is going to be, well, from this again, if I draw my sine graph, which looks something like this, y equals sine x, then again, if I want to then go on to plot y equals sine of minus x, then that again is going to be a reflection on the y-axis, which would then give me this. Like so. So in terms of, and obviously that red is like so. So from this, what we can then establish is that what I've then got is that I can write y equals sine of minus x is the same as minus y equals sine x, because obviously then we're just reflecting it on the x-axis, which is going to be exactly the same. So therefore then what I've got is that y equals minus sine x, and all I've done there is just taken the negative over to the other side. So therefore then that sine of minus beta is going to be the same as minus sine of beta. Now from this, what I can then do is replace this into this here, so giving us that sine of alpha minus beta is going to be equal to sine alpha cos beta minus cos alpha sine beta. So the only thing that's changed is the sign in between the sine and the coses of the beta. And what that therefore gives us is our final trig identity of sine alpha plus minus beta equals, and it's going to be sine alpha cos beta, and it's going to be the same. So whatever sign is in the sort of bracket, in our initial bracket of sine alpha plus beta, that's going to be the same sign as in between our sine alpha cos beta and cos alpha sine beta. And there is our one trig identity proved. So now if I look at what cos alpha plus beta looks like, which we've already proved, so we know that that's cos alpha cos beta minus sine alpha sine beta. So again, if I then wanted to work out what cos alpha minus beta is, all I'm going to do there is change whatever is with the cos beta with where we've got a positive cos beta with minus beta, and then just change the signs, and what I end up with is cos alpha cos beta, because that's going to be the same. But then here I'm going to end up with sine alpha minus sine beta, and obviously two minuses then become a plus, so what I end up with is cos alpha cos beta plus sine alpha sine beta. And so from this stage here, you can see that when I've got a cos, the sign that's here is actually the opposite to what sign is in there. So my second trig identity proof is going to be that cos alpha, and then here plus minus beta is going to be equal to cos alpha cos, I can write it correctly, cos, no, that's even worse, apologies, end up with is cos beta, and it's going to be a minus plus. So whenever I've got a plus in that first bracket, it's going to be a minus between my coses and my sines, and if I've got a minus in the bracket, then it's going to be a plus when I've expanded it, and that's going to be sine alpha sine beta. And there is my second compound angle proof. Now when it comes to tan, again, what I'm going to do instead is, when I'm looking at tan theta or tan alpha minus beta, and what that's going to then prove is sine alpha minus beta over cos alpha minus beta. And I'm just going to prove in the exact same way, but what I then find out is that tan alpha plus or minus beta is going to equal, and it's going to be tan alpha plus or minus tan beta over 1, and then here it's going to be minus plus tan alpha tan beta, and there is my third compound angle proof. Now, although this may seem incredibly confusing in terms of the proof of where these trig identities, and you will find that these are going to be given to you in a formula book, but you might get a question where you may have to prove it. Hopefully this video makes it a little bit clearer as to where those trig identities do come from. Now, we'll do a video where we actually use these trig identities, and it's actually not that bad. So if you do feel like it's gone completely over your head, do not worry, because in the next video, I'll show you what the common questions are, and it's pretty straightforward.